this is the final polished mirror segment. And they polish it to a figure of about 20 nanometers. And then once that's done, we build up the whole system. And I think the next picture just gives you a better idea. So an individual mirror segment looks like this. And we have these 3 clusters of actuators that allow us to move the mirror in different degrees of freedom. And you'll see a video in a minute that shows how that works. And then to get all the mirrors exactly matched to each other, we also have this one in the middle, and that's attached to these rods at the edge. And now that moves in and out, and it allows you to change the radius of curvature of the mirror so that all the mirrors are matched. And time is pressing, so I'm going to skip by this one. So this just shows how you phase this telescope and how all the mirrors work. And you can, as you heard earlier, Hubble had this problem when it launched. One of the things we could do with this telescope is change the figure on orbit. And you'll see now, in just a second, there we go. So see, all the mirrors can be moved forward. This is called uncorrelated pistons. They all have different forward motions. You can tilt the mirror. So each of those actuator clusters on the mirror allow you to make these changes. So you use a very bright star as a source, and you essentially use a technology we developed to understand what was wrong with Hubble to figure out how to get this mirror perfectly aligned. And you can see, you can do some really drastic changes to these mirrors to get them into the right shape. So that's how we get this mirror working once it's in orbit. And that also has the benefit that we aren't expecting it all to stay perfectly aligned during the launch, where it sees extremely violent shaking. And to understand how to do this properly, we built a small telescope. This is what I call the Mini-Me JWST. And this is a Ball Aerospace, and they use this to test out the technology. Now, coming back to the sun shield, how do we get that telescope cold? This picture shows you exactly how it works. So this is the sun shield, this is the telescope, and the sun's over here. So basically, all this stuff is in the dark, never sees the sun, and it basically just passively cools down to 40 Kelvin. And that's how we keep it cold. But as I said, this technology is very interesting, and this is a full-size, these are real people here, and that guy just there, sticking up through the middle. This is a full-scale prototype of one of the membranes, and you can see they're trying different ways of stitching it here, so one half looks different to the other. But this is what it looks like, and this thing's as thin as a candy wrapper. So we have 5 of these, and they all have to be packaged properly. And then for launch, as I said, we have to fold it up. So this is what JWST looks like when we launch it. This is the Ariane 5 fairing, and it folds up like that. And once we fly, everything has to come out, and this is how it does it. And we will all be biting our nails while it does this. So first of all, once it's out, we put out the solar panels and the communications, then the sun shield pallets. You saw the telescope move up there. That's so it's not sitting on top of this hot bus. Then we open covers on these sun shield pallets, and then these side booms pull it out. So you see we start with one side, then the other. And at this point, they're not separated. So then we raise this separator. You can't see it in here to open the middle up. And then each of the layers are pulled up these rods so that they're separated. You see them separating out just here. There you go, 5 layers. And then finally, we unpack the telescope. So there are 2 side panels, one here, one there. And they will fold round, and the secondary mirror folds down and out. And these things all lock into place once they're deployed. So that's how we unpack this telescope once it's been flown. Okay, so just to finish up, I haven't said much about the instruments, but I did just want to quickly highlight what they do. There are 4 instruments. NIRCam is the American instrument built at Arizona. And that will do the very deep, wide-field imaging that we need to do first light. And it will also be able to take images of those disks I was telling you about. it also does one other thing, which is it does the measurements so that we can phase the mirror. So it's kind of a multi-purpose instrument. The European instrument is called NIRSpec, and this is being built by a consortium of European countries under the management of the European Space Agency based at ESTEC. And it will basically do the follow-up. So we take these pictures, we find our candidate very faint first light galaxies, and then we want to get spectra of about 100 of them at a time. And the reason we want to do that is because it takes us about 10 million or more seconds to take a spectrum of each one of these things, we think. So you get much better science and much more science for your money if you can do about 100 at a time. So we figure out where our targets are in the field, and then we open microshutters that correspond to those targets and collect about 100 spectra at a time. And that's how we will do these follow-up work to confirming that we've imaged these first light objects. And then we can also do other things with NIRSpec, and the spectroscopic work on the planets is one of them. The Europeans are building the mid-infrared instrument in collaboration with the Jet Propulsion Lab, and that will take the mid-infrared images that complement these images and allow us to see if a first light object has second or third generation populations, which would mean that it's not a first light object. So it will be able to complement the first light science, and then it will be able to do very detailed studies through the dust of these forming planetary systems and forming stars. And then finally, the Canadians are building an instrument called the Fine Guidance Sensor. And what that does is it points the telescope. So JWST will have the same pointing that Hubble does. And we do that by taking images and finding a star in that image and then tracking on that star. So the Canadian instrument does that tracking. And then finally, just to finish up on the technology, one of the things we learned from Hubble is you have to do what's called an end-to-end test. You can't just build this thing, pack it up, and launch it, and not do an end-to-end test to confirm that it's going to work the way you want. And people always say if we'd have done an end-to-end test of Hubble, we would have learned that there was spherical aberration before we launched it. So the first thing we learned from Hubble is you have to do an end-to-end optical test. The other thing we learned from Hubble is you have to believe the cross-checks that you do as you go along and use those as a kind of monitor to see if what you're doing makes sense. And both those things weren't done with the Hubble mirror, and we got spherical aberration. The problem with JWST is that it's very big, and again, it's cryogenic. So not only do you have to do that end-to-end optical test, you have to do it at 40 Kelvin. So we searched high and low, and then finally we found this chamber, and there is actually a guy standing just in front of this box here. So a human is about this big. This is called Chamber A. It's a national monument, believe it or not, in Houston at the Johnson Space Flight Center. And this is what they used in James Webb's time to test the Apollo landing modules and various bits of the hardware that went to the moon. So once upon a time, they would roll command modules in here and do testing of them in vacuum. So we picked this one for JWST because the mirror fits inside. Now, we can't do the sunshield test in there, but we can set up the mirror, and we can set up an optical system, and we can put light through the whole instrument, through the mirror, and then back down into the instruments, and do a measurement to confirm that we have the image quality that we think we will have, and do it at 40 Kelvin. So the downside of this is it's going to take us about 2 or 3 years to do this test, but we'll do it because unlike HST, we can't service JWST, so we have to get it right first time. So that's what we're doing for an end-to-end test. And again, this is with the door shut. So we'll wheel this hardware in, shut the door, and it will take, about, I think, 1 to 2 months to get it pumped down and cooled to the right temperature. And of course, you need to make sure these tests go right because, it takes you 2 months to start, so you don't want to have to go back and open the door to plug something else in or whatever. So it's a very complicated test, and it's, major challenge for logistics and getting all the hardware in place at the right time to do this test. And I'm going to finish up coming back to this what will JWST discover theme, and I just wanted to point something out that I think is very special about Hubble. And when we built Hubble, we built it to do this set of problems, to understand the distance scale of the universe, measure Hubble's constant, to image or at least prove the existence of giant black holes in galaxies, to measure emission lines in active galaxies, to study the intergalactic medium, and to do chemistry of the interstellar medium. And it turns out that when you look at the sort of most significant science that Hubble has done, and using citations in published journals is a good way of doing that, the things that people cite, of course, include these, but they also include a whole bunch of things that people didn't even think about when we first built Hubble. And just to give you an example, the creation of galaxies, the ultra-deep field that I showed you is one example of that. I mean, that's just such a significant piece of work that Hubble's done there. Hubble did a lot of the heavy lifting in the discovery of the acceleration of the universe by measuring a lot of the very high redshift supernova that couldn't be done from the ground. It's also been able to image the sources of gamma ray bursts. It's been able to take pictures of debris disks and infer the presence of planets from the structure of those disks. And it's been able to get the measure molecules and in the atmospheres of several exoplanets. So at least 5 of the 10 things that Hubble's done, people weren't even thinking about. And coming back to that theme about, how Martin Harwitz said astronomical discoveries, are a function of the new capabilities that you bring online, we expect that in addition to what I've told you today, JWST will be able to do all this new science that's really very, at the moment, we haven't even thought of. So it will make lots of very new discoveries and lead us in new directions that we can't imagine right now. And I will finish there. Thank you.
Grazie Mark. Siete certamente resi conto di quanto sia un'impresa complicata costruire un telescopio spaziale da portare a 1,5 milioni di chilometri dalla Terra, che deve funzionare, per chi non ha pratica, con i 40 gradi Kelvin, significa 230 gradi sotto zero, e tutti gli strumenti devono funzionare perfettamente e arrivare a delle scoperte. Quindi è un'impresa davvero titanica, grande, però gli scienziati ci credono, ritengono che sia possibile utilizzarlo, e a questo punto credo che sia arrivato il vostro momento. Avrete certamente qualche curiosità in più da soddisfare e Mark è qui pronto a rispondere.
Volevo chiedere a Mr. Clampin, abbiamo visto più volte il telescopio spaziale Hubble riparato in orbita dagli astronauti a 500 km circa dalla Terra. Questo telescopio nuovo verrà posizionato a 1,5 milioni di chilometri dalla Terra, ma se accadesse un imprevisto, come possiamo portare gli astronauti con i mezzi attualmente a disposizione a questa distanza? Questa è la prima domanda. La seconda domanda è più politica, è questa. Lei ritiene che questo momento economico particolare, con questo enorme stanziamento del governo americano per sostenere le banche in difficoltà, uno stanziamento veramente su scala italiana incredibile, possa avere dei riflessi negativi anche sul lavoro, sui finanziamenti per la NASA e quindi anche su questa particolare missione? Grazie.
Okay, to answer the first question, Hubble is really unique in that we've been able to service it several times. The majority of space missions that have flown do not have that option. And as you build and design these missions, you essentially account for that. So Hubble was designed to be serviced from the very beginning, and we've luckily been able to exploit that capability.